We will show you today the techniques for measuring the refractive index, and we start with the Abbe refractometer and the Becke line method. So for the Abbe refractometer, this is the device, and if you remember, it exploits the total reflection of the light. So the fact that when you go from high refractive index materials to low refractive index materials, an angle exists above which the light is totally reflected and you don't have any light transmitted through or refracted through the other materials. So this is the how the Abbe refractometer works. So you have the two prisms, the illuminating prism, and you send the light through this hole, okay, and you have the surface which is rough, and you have the refracting prism. In this case, you see that the surface is well polished, okay. So you just have to place a few drops of the liquid here, close, just lock it, and send the light through. And what you have also a thermometer. You can add the thermometer to check and to measure the temperature of your sample, okay. And keep in mind that the refractive index depends also on the temperature of your sample. What you have also, you have your eyepiece where you look through, and you can see the transition, as we will see later during the measurement, between the dark and light areas. Basically something like that, okay, this dark and light, okay. And then you have another knob that, rotating it, you can compensate for chromatic effects. And then what you have to find is, with the big knob here, just rotate and decide, find the total the angle of total refraction. Since the refractive index of the prism is about 1.7, it means that this is the upper limit of your measurement. So very simple equipment, very fast measurements. If you want to measure a solid, which is not really common in this case, but you just you just use the refractive prism and send the light from the bottom here. But in this case we will measure liquids, and we will don't consider this option. If you remember, the refractometry is also useful to measure the content of solid, and in particular sugar, in fruits or other elements. So we will also consider this measurement today, measuring the sugar of different fruits. So I think we can start with the practical measurements, and we will have a light source and a camera looking through the eyepiece. So we can start now with the measuring the refractive index of water. You have here the Abbe refractometer with a camera, and you see there the image. I would like to show you that you have the refractive index here, okay, and upper here there is the percentage of sugar. We will then move later on to see clearly this scale, and here the cross, and what we have to do is to find the transition dark light and place it in between the cross. Okay, so just take a few drops of water, okay, and place on the refractive prism, then closed. Okay, so we see now that it's white, and so almost all light, and you see that we can move with this big knob the transition dark light. Okay, and you see that the refractive index increases, so we have to reach the transition. You see the other one is to compensate the color, but in this case was fine here. So what we have is for water 1.332. Okay, so if you remember, water was approximately 1.33. This is pure water, and this is the correct number. Keep in mind that we are using white light, so we are measuring an average refractive index of the liquid in the visible. And as you can see on the upper level, you see that it corresponds to almost 0% of sugar. This is, of course, this is clear since we have just pure water. Okay, so we can then move to a second sample. Okay, liquid sample. We just have to dry the surface, and now we have this is isopropanol. Okay, if you remember isopropanol, this is an alcohol. Okay, very simple, and later we will measure also the toluene, but let's start with the isopropanol. Okay, again a few drops, okay, on the refractive prism closed, and again we don't see, we just see light, so we have to find the transition, and we can go in the two directions, but of course I think the refractive index will be larger than water, and see the transition. We can fix and see if we can make better. Okay, this is probably slightly better. Okay, so isopropanol, we have 1.377, so a slightly higher refractive index than water. This is understandable since we have, if you can see here, the structure also methyl group, so more polarizable group than just simply OH, and but just quite limited refractive index. What we can say, if we read the other scale, we have about 27% of sugar. Of course, in this case it doesn't mean anything, since we are measuring the refractive index of a different liquid and not the refractive index of a solution of water and sugar. But we can say that the isopropanol has a refractive index equal to a solution of water and sugar with 27% of sugar. Okay, we can clean again. And take the toluene. So toluene is an aromatic compound. Okay, so basically we could expect to have a higher refractive index since we have pi electrons that are polarizable. Okay, and this is the situation. Again, we see all the area illuminated, so we are far from the refractive index. We can move up and see nothing. We are 1.4, 1.43, and okay. Now we see that the transition is quite good, and just place the transition on the X. Okay, maybe here. So we have 1.495, so much higher than the refractive index of isopropanol and water, but this is not strange since it's aromatic. Let's go back here. Aromatic, pi electrons, highly polarizable, and so we expect to have a higher refractive index. Okay, so, and keep in mind that in order to have this refractive index, you must prepare a solution with about 82% of sugar in water, so very high content of sugar. So with the toluene, I think we can stop with the solvents or different liquids, and we can move on considering the refractive index, or differently the content of sugar in water solutions. And if we go back here, if you remember, we have this brick scale, okay, so the percentage of sugar and the corresponding refractive index, and you know that you have for different fruits or vegetables, you have a different value of bricks degrees for where they have ready, and so this is really important, as we saw, for understanding the ripeness of such liquids and vegetables and fruit. So we can do the same, and we have here. Okay, so what we start with is okay, mandarin, okay, and then we have a lemon, and we have also a kaki. Okay, so we will test the three, and just take some juice of the lemon, okay, with the syringe, and once we have it, we just place the few drops on, again, the refractive prism. Okay, we have the drops of lemon juice on the refractive prism, and now of course it's fully dark, because we don't expect that lemon has a content of sugar of 80 something percent. We have to go at a lower content of sugar, much lower. I think it's not very sweet, the lemon, as you know. And here we have, okay, so we have 7.5% of sugar in lemon, and the refractive index is 1345. So of course larger than the refractive index of pure water. Not we don't have a large amount of sugar in lemon. Let's see if with the mandarin, that I mean, usually it's more sweet than the lemon, if it's if we will measure a higher refractive index and higher content of sugar. So again, we can take some juice of mandarin, okay, let's see. Okay, actually we have a different refractive index. This is positive. We are here almost on the intersection of the two lines. Okay, so with the mandarin we have 14%, so almost the double of the content of sugar of lemon. This is positive. It means that the instrument works, and the common feedback we have from fruit is exactly what the Abbe refractometer measures, and the refractive index is 1.3545. So of course a larger refractive index. So in this case we can clearly see the different fruits have different content of sugar, and this is predicted by the measurement with the Abbe refractometer. As a last example, we consider the Caki. It doesn't look really ready to be eaten, and another point is it's not a real liquid. So what we can do is take some pulp of the Caki and put on the refractive prism. Again, we will see if the content of sugar will be larger or lower. Again, we don't have the same refractive index. We see that we see more light than dark, so it means that the refractive index here is smaller than expected. So let's go up, try to find a nice transition. Okay, here we go. We have 20% of content of sugar. So again, for the Caki we have a higher content of sugar as expected in comparison to mandarin. Keep in mind that maybe when the Caki will be ready to be eaten, the content of sugar probably will be much higher, 30–40%. The refractive index is 1.364. So we see the important things about the Abbe refractometer is very fast, give you direct measurements of the refractive index and content of sugar in this case in different fruits. And as I think we finished with the Abbe refractometer, and we can move on the Becke line method. So as for the Becke line method, if you remember, it is very simple. It is useful for solid sample. You just have to take a piece of solid sample and put on liquids of different refractive indices, and if you can see the solid sample inside the liquid, it means that the two medium, solid and liquid, have a different refractive index. Once they match the refractive index, you cannot see the solid sample anymore. So here an example, very high difference in the refractive index, you clearly see the solid sample. Decreasing the difference in the refractive index, you see that you can just see weakly the edges of the solid sample. If you remember, the Becke line was just the way to understand if the liquid or the solid has the higher refractive index. We cannot do the real experiment, but what we can do is just take two beakers, one with water and the other with toluene, and see if a piece of glass, in which case the piece of glass has a similar refractive index. So we take water and we just put the piece of glass, and you can clearly see that it's really visible, the piece of glass. So it means that we know water has a refractive index of 1.33, the glass is about 1.5, so this is something expected to find. Okay, let's try with the toluene. Okay, this is the toluene. Okay, this is the piece of glass, and you see that almost disappear. Okay, but the toluene, as we saw before, has a refractive index of 1.49 something. Glass is about 1.5, so we clearly see here disappearing. Okay, so this is really nice. This is something you can do also with your friends, but not just using toluene, but for example water and sugar, and prepare a solution with 1.5 refractive index and try to make a piece of glass disappearing. So you see, it's again very simple. The real Becke line method is usually performed using a microscope, but this is the principle of work, and I think this is enough for this technique.